In this video, we are going to discuss how to calculate induced EMF and current using Faraday's law whenever there is a change in magnetic field. The question says, a coil constituted of 100 windings, each of surface area A equals 4 times 10 to the power negative 3 meters squared, is placed in a magnetic field whose magnitude varies according to the relation B equals 6t squared plus 4. The normal vector to the plane of the coil is parallel to magnetic field. Calculate the induced potential difference in the coil at t equals 1 second. So here in this question we have a coil that has number of windings capital N as 100. The area of the coil is 4 times 10 to the power negative 3 meters squared. The normal vector, which is also the area vector, is parallel to magnetic field, so the angle theta is 0. And we need to find the induced EMF at time t equals 1 seconds, where the magnetic field B is given as a function of time 6t squared plus 4. Now we know from Faraday's law, induced EMF is given as negative d phi by dt, where phi is the magnetic flux, which you can write as negative d ba cosine theta over dt. Now out of this expression, only magnetic field is changing as a function of time. So we can take a cosine theta outside of the derivative. So we get negative a cosine theta dB over dt. Now substitute for b, we get negative a cosine theta derivative of 60 squared plus 4. Then we can substitute for a. Area will be the area of the coil, which is 4 times 10 to the power negative 3 into cosine 0. Derivative of 60 squared will be 12t. Derivative of 4, which is a constant without t, will be 0. Now substitute for time t, you get induced EMF to be equal to negative 4 times 10 to the power negative 3 into cosine 0 into 12 times 1. That gives you the induced EMF as negative 0.048 volt, or you can write this as negative 48 millivolt. The negative sign here only indicates that the induced EMF opposes the change in magnetic flux in the coil. Now let's discuss question 9.30. An 8-ton coil has square loops measuring 0.2 meter along a side and a resistance of 3 ohm. It is placed in a magnetic field that makes an angle of 40 degrees with the plane of each loop. The magnitude of this field varies with time according to B equals 1.50 t cube, where t is measured in seconds and B in Teslas. What is the induced current in the coil at t equals 2 seconds? So here we have the number of turn N as 8. The length of each side of the square loop, which we can write as L, is 0.2 meter. And since it is a square loop, its area will be just the length squared. Resistance of the loop is 3 ohm. And the magnetic field through it varies as 1.5 t cube, which is a function of time. And they said that the magnetic field makes an angle of 40 degree with the plane of each loop. So if this is the plane of the loop, magnetic field is making an angle of 40 degree with the plane. So with the area vector, it will make an angle of 50 degree. So I can write my angle theta to be 50, which is 90 minus 40. We need to find what is the induced current at time t equals 2 seconds. Now, induced current I can be found by dividing induced EMF with the resistance R. So first we will find what is V induced and then calculate the current. We know from Faraday's law, induced EMF is negative d phi by dt. Phi you can write as negative d ba cosine theta over dt. Since only magnetic field is changing as a function of time, we can take A cosine theta as a constant outside. So negative A cosine theta dB over dt. Now substitute for B, we get this as minus A cosine theta derivative of 1.5 t cube. So negative A cosine theta derivative of 1.5 t cube will be 3 times 1.5 into t squared. Now this is induced EMF. We need to find current. So now we will divide this term with the resistance R. So we get the current I as V induced over R, which is negative A cosine theta times 3 times 1.5 times t squared over R. Now substitute the value. A is length squared. Length is 0.2, so 0.2 squared into cosine 50 into 3 into 1.5. T is 2 seconds, so 2 squared over R, which is 3 ohm. And we get the current I as negative 1.23 ampere. Again, the negative sign only indicates that the induced current is opposing the change in flux. Next question. A loop of wire enclosing an area A is placed in a region where the magnetic field is perpendicular to the plane of the loop. The magnitude of the magnetic field varies in time according to the expression V equals V max e to the power negative AT, where A is some constant. That is, at time t equals 0, the magnetic field B is B max, and for t greater than 0, the field decreases exponentially. Find the induced EMF in the loop as a function of time. So here you have a wire loop that has an area A, and here the magnetic field is perpendicular to the plane of the loop. So if the magnetic field is perpendicular to the plane, that means it is parallel to the area vector. And here the angle theta will be 0. And we know cosine 0 is equal to 1. So when we are calculating the flux, which is VA cosine theta, since cosine theta here is 1, I can write the flux as just V times A. I need to find what is the induced EMF. We know from Faraday's law, V induced is negative d phi by dt, which will be negative dPA over dt. Since it's only the magnetic field that is changing as a function of time, I can take the area out of the derivative as a constant, so minus A dB by dt. Now substitute for B, you get minus A derivative of P max e to the power negative AT over dt. Now take derivative of this term. P max is a constant, so it remains as it is. Derivative of E is the same e to the power negative AT. Then we have to take derivative of the power here. So derivative of negative AT will be equal to minus A. So you get induced EMF to be equal to small a into the area P max e to the power negative AT.